Okay, this is the second video about rotation. We're going to be looking at the relationship between the angular and the linear variables. We know that they are analogous, and I briefly mentioned these relationships before, but we're going to look at it in a little bit more detail. So we've got our wheel moving with angular speed omega, and we can define the radius of the wheel to be r, and we want to know how fast a point on the rim is moving. So the speed v. Well, it turns out that if we measure omega in radians per second, v equals omega times r. It's really that simple. There's also one thing you notice here is that the farther out you go, the faster you move. So it's not all that difficult to deal with. Now there's also a similar relationship between angle and distance traveled, which is not the same thing as displacement. But if it rotates through an angle theta, the arc length, the distance traveled, is theta times r. And in fact, that's the very definition of the radian, is the angle measurement for which that is true. The reason it's not displacement is, let's say it makes one complete rotation, displacement 0, but the distance traveled is still 2 pi r. So very simple ideas there. Now what gets a little more complicated is when it comes to acceleration. We know that there's tangential acceleration. So you've got something going in a circle, and let's say that it is speeding up. Well, in that case, this point on the rim here will have a velocity in that way, that direction, and an acceleration, a tangential acceleration, causing that speed to increase there. So the tangential acceleration is the change in the speed per unit time, which is also the same thing as r times d omega dt, or r times alpha, where alpha is the angular acceleration. And that points in a direction tangential to the circle. Radial acceleration, or sometimes called centripetal acceleration, which you already know about, comes from moving in a circle. Now, even if it's not speeding up, the change in the direction of the speed will give you a centripetal acceleration or radial acceleration toward the center. And we already know AR is equal to v squared over r, and a little bit of algebra can tell us that that is equal to omega squared times r. So you have a tangential acceleration that arises from it either speeding up or slowing down. And you also have a radial acceleration that arises from the change in the direction, the fact that it's moving in a circle. And the net acceleration is the vector sum of those two. So the total acceleration is the vector sum at plus ar. Since ar is always perpendicular to at by definition, we can use the Pythagorean theorem, and it looks like that for the total the magnitude of the total acceleration. So now let's look at an example. This is problem 23 from your textbook. You've got an astronaut being tested in a centrifuge. The centrifuge has a radius of 10 meters, and when it starts, it rotates according to the function theta equals 0.3 t squared, blah, 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 blah. When t is 5 seconds, the question is, what is the astronaut's angular velocity? Well, we've got theta as a function of time, and angular velocity, or angular speed, is the time derivative of theta. And so that's going to be 0.6 t, and at 5 seconds, that's going to be 3 radians per second. Pretty straightforward. Now, linear speed, well, that's also very easy. V equals omega times r. We have omega, we have r. Becomes 30 meters per second. So even though 3 radians per second isn't that much of a change in angle, because the radius is a whole 10 meters, the actual speed is rather large. Now, to get tangential acceleration, that's going to be the rate of change in a linear speed, which is in turn going to be r times d omega dt. Now, omega is 0.6t, so that equals r times 0.6, and that equals 6 meters per second squared. And that value is going to be a constant throughout the whole thing. We can notice because omega increases linearly that we have constant angular acceleration and therefore constant tangential acceleration. The radial acceleration, however, is not constant because radial acceleration, or centripetal acceleration, is v squared over r. So the faster he goes, the larger the radial acceleration is, even though the tangential acceleration is constant. So v at 5 seconds, v is 30 meters per second. We've got to square that, divide by r, which is 10 meters, and we get a ridiculously large 90 meters per second squared. Well, it's ridiculous in the sense that it would be painful for the astronaut, but it is not ridiculous in terms of what these centrifuges can achieve. And moving on, I don't know what I intended to put on that page, but the questions that you should have for tomorrow are 5 and 6. See you next time.